this last video about section 11.1 on sequences, I want to talk about two important results. The first is the squeeze theorem. It's something you probably remember from Math 2a when you talked about limits. And the second is called the monotonic sequence theorem. So let's recall what the squeeze theorem says. This is covered in section 2.3 of Stewart's book on page 101. And it says if an, bn, and cn are real numbers in that order, an less than or equal to bn less than or equal to cn, whenever n is large enough. So you have a sequence of real numbers, like one for each n. You have an an sequence, a bn sequence, a cn sequence. And it doesn't have to be true that an is always the smallest one. Like maybe a1 is bigger than c1. But once n is big enough, we need an less than or equal to bn less than or equal to cn. So as you go far enough out, this is the order. And if the limit of an is the same as the limit of cn, and that's some real number L, then the limit as n goes to infinity of bn exists and is also equal to L. The idea is if the limit of the smallest things and the limit of the largest things are the same, then the limit of the middle things must also be that common limit, that the middle stuff is squeezed in between the lower sequence and the upper sequence, and they both have the same limit. So the middle sequence also gets squeezed or sandwiched into that middle limit. So there's a particular version of this that we'll use a bunch, which is, so same idea as the squeeze theorem. You don't need to worry about how to prove this. But here's a theorem that we can use, which is if the limit as n goes to infinity of the absolute value of an is 0, then the limit as n goes to infinity of an is 0 without the absolute value. So let's see why this is useful in our goal of understanding limits of sequences. Let's look at the limit of the sequence an given by e to the sine of n over n. This e to the sine of n is a little bit complicated because sine of n for some values of n will be near 1, and for some values of n it'll be near -1, and for some values of n it'll be near 0. But it fluctuates in a way that's not so easy to understand. But one idea is we can at least say that sine of n is always in between -1 and 1. So what does that mean about e to the sine of n? Well, we're taking e to something that's always at most 1. So that's at most e to the 1. And it's at least e to the -1. But that's not the function that we actually care about. E to the sine of n over n is always at most e over n. But it's at least 1 over e times 1 over n. So now we have 3 sequences that we can apply the squeeze theorem to. We can think of 1 over e times 1 over n as the an sequence, e to the sine of n over n as the bn sequence, and e over n as the cn sequence. And I'm going to pause and erase and then finish up the last details of this problem. Our goal was to understand the limit of this sequence given by an equals e to the sine of n over n. And we saw by using the bounds we have on sine of n that e to the sine of n over n is less than or equal to e over n and greater than or equal to 1 over e times 1 over n. So let's take the limit of this lower bound sequence and this upper bound sequence. And we see that the limit as n goes to infinity of 1 over e times 1 over n, well, the denominator is going to infinity. So we get 0. If we take the limit as n goes to infinity of e over n, we also get 0 for the same reason. So by the squeeze theorem, the limit as n goes to infinity of the middle sequence, e to the sine of n over n, also must be 0 because this sequence is squeezed between two other sequences where the limit is the same, and that limit is 0. Okay, let's do one more example. I'm going to erase the squeeze theorem to write this one. Let's look at the sequence an equals -1 to the n divided by n. So what is the absolute value of an? Well, it's the absolute value of -1 to the n over n. N is going to be a positive number. What happens when we put in the absolute value is we just get rid of the -1 to the n. That just becomes 1. So we just get 1 over n. And we know that the limit as n goes to infinity of absolute value of an, which is the limit as n goes to infinity of 1 over n, is equal to 0. So by this theorem right below, we know the limit of the absolute value is 0. So the limit as n goes to infinity of an is also equal to 0. So this converges just like this sequence converged as well. So I'll pause and erase, and then we'll talk about the last topic of this lecture, which is the monotonic sequence theorem. The last topic I would like to discuss in these lecture videos is called the monotonic sequence theorem. So in order to state this theorem and explain what it says, we have to first make a bunch of definitions. Some of them are clear, but it's good to be very precise with these definitions. So a sequence an is increasing if an is always less than an plus 1. So that means as you go from n to n plus 1, the element of your sequence gets bigger. Your sequence is decreasing if an is always bigger than an plus 1. As you go from an to an plus 1, the element of your sequence gets smaller. And a sequence is monotonic if it's either increasing or decreasing. So monotonic means that what you're not allowed to do is like go up for a while, then come down. You're either always going up or always going down. Okay, that's monotonic. It just means increasing or decreasing. A sequence is bounded above if there's a real number, capital M, where an is less than capital M for all n. Meaning, no matter how far out you go, there's some number that's bigger than every element of your sequence. A sequence is bounded below if there's a real number, little m, with little m less than an for all n. Meaning, no matter how far out you go, maybe your sequence comes down for a while, but it never goes down as far as little m. Little m is always below everything in your sequence. And a sequence is bounded if it is bounded above and it's bounded below. So there's some lower number and some upper number so that every an is between those two numbers. So we know what monotonic means, and now we know what bounded means. The monotonic sequence theorem, which is on page 702 of Stewart, says that every bounded monotonic sequence converges. It doesn't say what it converges to, but it converges. Okay, a few words. First, what is an example? Well, an equals 1 over n. That's a sequence. An is always between 0 and 1. So it's bounded below by 0. It's bounded above by 1. Or maybe a1 is equal to 1. So here I wrote less than instead of less than or equal. So it's bounded above by like 1.1 or 2 or some other number. And this sequence is decreasing. As you go from an to an plus 1, the numerator stays the same and the denominator gets larger. So the sequence is decreasing. That means that it's monotonic and bounded, so it converges. We already knew that this converged. So here, the monotonic sequence theorem doesn't help all that much. And that's actually common here. We're not going to use this result that much in this course. Usually, for any sequence where you could apply this theorem, we're going to be able to tell that it converges in a more direct way by looking at the limit. The tricky part here is actually often showing that your sequence is monotonic. Like, how do you show that a sequence is increasing or decreasing? Well, often what you can do is if your sequence is an, you do the kind of thing that we did when we talked about L'Hopital's rule. You find a function f of x where f of n equals an. And then, how do you show that a function is increasing or decreasing? That we know from Math 2a or the equivalent, you can take a derivative and apply the first derivative test. So we're not going to use this result all that much, but it's something that you should know, so I wanted to mention it.